Okay, yeah, hello everyone, thanks for coming for this talk today. And I will talk about our SoK paper titled Parameterization of Fault Adversary Models, Connecting Theory and Practice. And this is a joint work with Svedla and Vanci. And this paper was actually published at CTRSA, and it was also presented in May. So in this work, we consider fault attacks and countermeasures specific to symmetric key cryptography, and also specific to ASICs only. And in this work, we propose a parameterized fault adversary model such that it encapsulates the control span of an adversary over an ASIC board. And based on this model, then we discuss how well the theoretical assumptions made in fault attacks and countermeasures align with practical realities. So in a way, we also discuss how well actually we protect against physical fault injection mechanisms. Okay, so yeah, let's start with the fault attacks. They are active kind of physical attacks against the implementations of cryptographic algorithms. In this kind of attacks, adversaries interacting with a device, and they are intentionally disrupting the computation using some physical fault injection mechanisms. And this might be clock voltage glitches, EM waves, or laser fault injection. And after the adversary is injecting faults to the circuit, then the device can give, for example, wrong output, or no output at all, or still a correct output. And after all these reactions, the attacker is taking all of them, and then they're applying some kind of mathematical analysis to deduce some kind of secret information from the device, such as the secret key that is embedded in the device. So a fault attack simply consists of two steps. The first step is physically injecting the fault. Here, the adversary is making like real physical changes in the circuit, such as changing the outputs of the gates or changing what is written inside the registers. And in this context, the adversarial model is used to formulate an adversary doing this step. For example, this model says like how many faults the adversary is injecting or which locations in the circuit are like interacted by the adversary, or what are the effects of the injected faults. And as I said before, the injected faults are then mathematically exploited by the fault injection adversary. And this step, the exploitation of the injected faults, actually based on some assumptions regarding the physical fault injection adversary. So what happens here is that the mathematical analysis methods say, so there's this kind of adversary, and they are injecting this kind of faults in the circuit. They are making this kind of changes. And then if this happens, by using this analysis method, we exploit the injected faults, and then we find the secret information in the circuit. And similarly, we have the countermeasures that are proposed against the fault analysis methods. So they are developed to protect against this kind of attacks. And in a similar way, they also based on these assumptions regarding the fault injection adversary. And what happens here is that if this kind of adversary realizes this kind of fault scenario, like injects this many faults and does this many changes in the circuit, then by doing this, we render those injected faults unexploitable by the adversary. So the important point is that both mathematical analysis methods and the countermeasures are based on similar assumptions regarding the physical fault injection adversary. And so in this work, we make some new notations to make the distinction in those assumptions. First, we use the physical adversary model to formulate the physical adversary that is making the changes in the circuit. And we use the analytical adversary model to formulate the assumptions made in mathematical analysis methods, the fault exploitations. And we make use of the term mitigative adversary model to formulate the assumptions made in countermeasures. So in practice, an attacker using a physical fault injection mechanism can realize many different fault scenarios on the circuit, like with different kind of faults, with from 1 to 10, many faults and all. But as we're gonna see later in the presentation, that the proposed mathematical analysis of them do not really benefit from all those capabilities offered by the physical fault injection mechanisms. And also each fault analysis method depends on like different kind of properties of the injected faults. And so this makes the assessment of the cryptographic implementations a bit hard, because you check this mathematical analysis method and then you check that, but it might be unsecure against this one, so you never know if it's fully secure or not. And on a side note, the countermeasures are mostly developed to protect against specific mathematical analysis methods, but not the physical adversary, for example. So this also makes it hard to know that if we are protecting against these attacks or not, or maybe in practice someone is going to come and break the security of the implementation. So it would be best if we have the fault model that we can formulate all those adversary models so that we can compare them and all. So in this work, we propose a parameterized fault adversary model such that we can encapsulate the capabilities that an adversary can have using the physical fault injection mechanisms. And based on this model, we analyzed all the capabilities of the physical fault injection mechanisms and the analytical adversary models and mitigative adversary models. And then we checked if they are really aligning with each other, or like if we think we protect against them, but actually we don't protect against them, or do we benefit all the capabilities we can have in practice. And let's continue with the proposed model. And we chose the following parameters such that we can precisely model the physical adversary. And the first one is the number of fault injection events. This is the number of times that the adversary is using the injection mechanism to inject a fault in the circuit. And this might be beneficial, for example, when adversary is injecting multiple faults to bypass a countermeasure. For example, if there's a duplication, then the adversary needs to inject 2 faults into 2 redundant parts so that the fault cannot be detected. And the next one is fault location. And the adversary can have precise, loose, or no control over the fault location. Precise control implies that the adversary can choose a specific gates or registers in the circuit to inject a fault. And loose control means they can target like a cluster of gates or registers, but which ones of them are going to be affected is actually unknown by the attacker. And no control means that they have no control over the fault location. And the next one is fault timing. This is also similar to the location. They might have precise control, which means they can inject the fault into the certain operation or certain clock cycle. And loose control means they can target a number of clock cycles or operations, but they can't really choose the specific one. And no control means they have no control over the fault timing. And the number of affected bits, this is the number of bits that are directly affected by the injected fault. And duration of the injected fault, this might be transient, persistent, or destructive. And a transient fault is effective for a limited period of time until the circuit recovers the actual value again. For persistent fault, the period is a bit longer, so the fault is effective until the value is explicitly rewritten. For destructive fault, it destroys the physical layer, so you can't really reverse the fault back. And the targeted gate type, an adversary can target a memorial gate, a combinatorial gate, or they can target both of them. And fault type, this is the effect of the injected fault in the circuit, like what the fault is changing in the circuit. For example, a set fault, it changes the value of the targeted bit to 1. A reset changes it to 0. Or it might be a flip fault, which means the value was 0 and now it's 1, or it was 1 and now it's 0. Or the fault can be random, like any of them randomly chosen. Or a custom fault type, which means the adversary can target a gate and then they can apply the specific mapping of their choosing instead of that gate. And now that we went over the proposed adversary model, now we can start looking at the physical fault injection mechanisms and see what an adversary can have in real life. And first we have clock glitches and voltage glitches, and they both target the longest critical path in the circuit in a way that clock glitching shortens the clock period, and voltage glitches increases the propagation delay of the transistors. So at the end, there's not enough time to do the full propagation and stabilization, so we have the wrong value at the end of the registers. And using these mechanisms, it's actually not really easy to precise the targeted location in the circuit, because which gates are going to be affected depends on the processed data and the underlying circuit at the time of the fault injection. so the attacker cannot really inject a precise fault using them. And the next one is EM fault injection. EM waves causes a race in between clock and input signals in the circuit. So if the clock signal arrives first, then there might be a faulty sampling at the registers, which causes a fault in the circuit. And using an EM fault injection, an adversary can target a precise location in the circuit, but it's kind of loose because it's a cluster of gates, and the adversary cannot really say, and this gate are going to be affected. So it's kind of unknown. But it has higher spatial resolution than the glitching because eventually the adversary is able to target a specific location. And then the laser fault injection comes, and this has the highest spatial resolution because using this mechanism, an adversary can choose specific gates and registers to inject the fault. So if we sum up all of them, with glitching, the adversary cannot really choose the location in the circuit. And with EM fault injection, it's a loose control, so they can target a cluster of gates. And the laser fault injection has the highest precision, so they can target specific gates and apply the specific fault types using this mechanism. And so to sum up everything, like compare with each other, all the physical fault injection mechanisms target a fixed location. So an adversary using these mechanisms cannot really adaptively change the location of the fault injection during the encryption. And they only target a few locations, like not the whole circuit. And they can inject several fault injection events. And this can also happen within a cycle. And they can also possibly last several cycles. And if we want to group the mechanisms, then we can say that the ones that has high precision and small target area, and the ones that have low precision and large target area. And let's see, what does it mean? And the mechanisms that has high precision and small target area typically target the specific gates in the circuit. And they're also able to inject the specific fault types, like they can choose set or reset faults. But the thing is, the fault is limited to a few gates. So the number of gates that are affected by the fault is upper bounded. And we can give laser fault injection as an example to this group. And the next group is low precision and large target area. And the mechanisms that are in this group affects more adjacent gates than the ones that are initially intended. And the number of the gates that are affected by these mechanisms are unlimited. And saying this, they don't have the high precision, so the adversary can inject only a random fault using those mechanisms. And from the last slide, we can say that glitching, clock voltage glitching, and EM fault injection are the examples of such mechanisms. And now that we know how an adversary injects the fault to the circuit, and now let's see how they are actually exploited mathematically. So the fault analysis methods take the injected faults and they find some kind of mathematical methods to exploit the injected faults to get the key, for example. And if they also get help from the side channel information, then it becomes combined analysis methods. And these are the three fault analysis methods that attracted the most attention, and they're kind of base of other attacks as well. And the first one is differential fault analysis, DFA. In this analysis method, the adversary gets two different ciphertexts, and one is correct and one is faulty from the same plain text. And the faulty ciphertext is obtained by injecting a fault in the computation. And then the adversary is exploiting the differential information obtained from those two ciphertexts. And the next one is statistical fault attacks, SFA. In this one, the adversary is injecting a fault to an intermediate variable to create a bias. And then this bias creates a non-uniform distribution when that intermediate variable is obtained from the collected ciphertext. And in SFA, the adversary collects the wrong ciphertext, the faulty ones, and then they obtain the distribution of the intermediate variable. And if it's non-uniform enough, then they can do the key recovery using this information. And so both DFA and SFA makes use of the wrong ciphertext, which means they make use of the effective faults, meaning they inject a fault and the fault propagates to the output, yielding a faulty ciphertext. And SIFA, statistical ineffective fault attacks, it makes use of ineffective faults, meaning there is a fault injected, but the output is still correct. So the injected fault didn't propagate it to the output. And CIFAR works just same as SFA, but in CIFAR, the adversary collects the correct ciphertext instead of the faulty ones, and then they check the distribution of the targeted variable, and if it's non-uniform enough, then they can do the key recovery attack. And now let's see what is common in the analytical adversary models when we map them to the proposed adversary model. So first, they demand only a fraction of the capabilities provided by the physical fault injection mechanisms, because they mostly exploit single injection and even faulting on a single bit. So it's always limited how many bits are affected. But we have seen that, for example, with clock and voltage glitching, actually we can affect so many gates in the circuit. And also what is interesting is most of the attacks assume the classical analytical adversary model. And in this model, the attack is bounded. So the adversary is allowed to inject only a limited number of faults. It's precise, so they can inject the fault type that they desire, but it's always upper bounded. And we have seen that the fault attacks and how they're exploited. And now let's see the protection mechanisms against them. And instead of talking about specific countermeasures here, I will give this description of main protection mechanisms. And redundancy combined with masking is the most common approach to protect against fault attacks. And redundancy is they just obtained in some way redundant computations so that the fault can be detected. And masking is the most well-known approach against side-channel attacks, and it randomizes the computation. And in this way, it might also help to protect against fault attacks because the randomized computation can randomize the effect of the injected fault. And now let's see how this can be realized in countermeasures. And the first way is to implement error detection or correction codes, and this can be also simply a duplication. In this kind of countermeasures, the developers mostly put error checks in some specific points in the implementation, but this is mostly done by putting the error check at the end of the circuit. But when I set the ineffective faults that do not propagate to the output and gets lost somewhere in between, doing this simple error check at the end cannot really catch the ineffective faults. So most of the countermeasures that use error detection and correction codes, as long as they do crazy amounts of error checks, they misses the injected faults. And in pickable circuits, PAR-TI, transform, and encode are such examples of the countermeasures. And the other way to implement redundancy is to use message authentication codes, and these are MAC tags. And MAC tags are the additional pieces of information that are associated with the data to ensure the integrity of them. And M&M and Kappa associates a MAC tag to each secret variable to keep the integrity of them. In Kappa, there is an error check in each multiplication, and M&M has a single error check at the end of the computation. So as you can imagine, Kappa protects against ineffective faults because the multiplication is the most simple operation in the circuit. And if you check all the multiplication, then it means you have error check in all of the circuit. But in M&M, since the ineffective fault doesn't reach to the end of the encryption, it misses. And the third way, I think the most interesting way to protect against faults is ensuring the fault propagation. So as I said, to catch the ineffective faults, either we need to check a lot of things in the circuit to catch them, or we need to make sure that all the injected faults propagate to the output so that with a single error check at the end, we can see all of them. And one of the countermeasures from Johan Diamond, actually they use the permutations, so the Toffoli gates, as the most simple building blocks in the circuit. And what happens is that if the input of the permutation is wrong, then with the permutation properties, they can make sure that the output is also wrong. Because if the input is wrong, then there's no way that it can be mapped to the correct output. And another countermeasure, STATI, proposes a notion called stability, which ensures the present faults in the input are always propagated to the output. But you don't really have to use a permutation for that. And when we mapped the mitigative adversary models to the proposed adversary model, and what we saw was they actually align really good with the proposed mathematical analysis methods, but they don't really protect against the physical fault injection methods, because they mostly provide protection against bounded order of attack, but there are some exceptions to that, such as M&M and kappa. And interesting that M&M and kappa allows the attacker to inject unlimited number of faults if the faults are random. So the thing is, there are a lot of countermeasures also which provides provable security, which is really nice because 100% you can rely on them. But the thing is, they offer this security within a really restricted mitigative adversary model. It says that the adversary is allowed to inject n faults, and d bits are going to be affected by that, and the numbers n, d are mostly like 1, 2, or 3. Yeah, they're really small. And that being said, it might be the case that the countermeasures are also over-designed, because as I said, for example, in kappa, like unlimited number of faults can be injected, but actually in practice, we don't really need unlimited number of faults to break the security of the implementation. So we want to protect against them, but we need to be careful that we are also not using a lot of resources to protect against them. So we can conclude it with saying some last words about everything. So in such an analysis, we have the order of the attack, because if we increase the order of the attack, then the mathematical analysis gets almost impossible. It requires a lot of resources. But in fault attacks, there's no such attack bound. I mean, it's really hard to inject a fault to the circuit. If an adversary wants to inject 10 faults to 10 specific locations, it's of course really hard. But as long as the faults are injected, then the mathematical analysis part is not that hard, because if there are 10 redundant parts, then with 10 injected faults, they can bypass the countermeasure very easily. And so, as we have seen, countermeasures might fall short in protection against the physical fault injection mechanisms, because they mostly protect against the proposed mathematical analysis methods, which exploit only 1 or 2 injected faults or really limited locations and all. But in practice, an adversary can do much more than that. And also, as I said in the previous slide, it might be the case that we are over-designing our countermeasures, and we think that we are protecting against physical fault injection mechanisms, but we are paying a lot and we don't really protect against them. And also one more note, in the fault analysis methods and countermeasures, what we have seen was the adversary models were not clearly defined. But for example, for mathematical analysis methods, if the adversary model is not clearly defined, then it's going to be really hard to replicate it in practice. And if it's not really clear in countermeasures, then it's really hard to know if we should make use of it or not, because we don't know against which kind of adversary they are protecting against. Yeah, that being said, I can conclude the presentation here. Thank you for coming.